Hi, I'm Bob. Welcome back to 5-Minute Econometrics, a program focusing on fundamental econometric concepts, estimation methods, and identification approaches. In previous videos, we have discussed t-tests for a single parameter beta in the model. Today, we will have a close look at testing hypotheses about a linear combination of parameters in the model. It involves more than one population parameter. I will introduce 3 ways to do the hypothesis testing with an example of the returns to education. The model relates workers' hourly wages to the number of years they have attended a 2-year college and a 4-year university. The outcome variable, log hourly wage, is in the logarithmic form, so the parameters capture the percentage change of hourly wages. We include work experience in the model as a control variable. The OLS results indicate that all explanatory variables are individually statistically significant at any conventional level because the p-values are 0 to 3 decimal places. It involves testing a hypothesis on a single parameter we have learned in past videos. Now, assuming we are curious about whether 1 year at a 2-year college gives the same returns to education as 1 year at a 4-year university. The null hypothesis is that beta 1 equals beta 2. Under the null hypothesis, 1 additional year at a 2-year college leads to the same percentage increase in wages as 1 more year at a 4-year university. The alternative hypothesis is that beta 1 does not equal beta 2. It is a two-sided alternative. The hypothesis concerned a linear combination of 2 parameters, beta 1 and beta 2. The t-statistic is based on the difference between them. The tricky part is to find the standard error of this difference. The first method to obtain the t-statistic is to define a new parameter and rearrange the model. We denote a new parameter, theta, as the difference between beta 1 and beta 2. The null hypothesis becomes theta equals 0, and the alternative hypothesis becomes theta does not equal 0. That is a familiar form of the hypothesis for a single parameter test. What we need to do is to rewrite the model so that theta appears directly as the coefficient of one of the explanatory variables. We express beta 1 as the sum of theta and beta 2, and then plug it into the original model. It leads to equation 2. The variables JC and experience remain in the model, and we construct a new variable equal to the sum of JC and ULIF. We regress the log hourly wage on JC, the new variable, and experience. Theta is the coefficient of the variable JC in the rearranged model. The OLS estimate theta hat and its standard error will be reported directly in Stata. We can also find the p-value. The idea for this method is to rewrite the model so that the linear combination of 2 parameters becomes one new single parameter in the model. In this way, we can use everything we have learned for testing hypotheses about a single parameter. The OLS results window shows that The estimate for theta is minus 0.01, and its t-statistic is minus 1.47. The p-value is 0.142. It suggests that the difference in return to education between a 2-year college and a 4-year university is not statistically significant at levels lower than 14% in a two-tailed t-test. For instance, it is not statistically significant at a 10% level against a two-sided alternative. We failed to reject the null hypothesis that these two types of schools provide the same returns to education at a conventional significance level. The second method to test a linear combination of parameters is to use the test command in Stata. We regress the original model. Then we type test and the null hypothesis JC equals unit. Stata will perform an f-test and report the p-value. The p-value is identical to that in the first method. The third method is to compute the t-statistic manually. After we regress the original model, we obtain the OLS estimates and their variance-covariance matrix. We can use the e-return-list and matrix-list commands to take a look at the values. The variance-covariance matrix is a symmetric 4x4 matrix that contains the variance of the estimates and the covariance between the estimates. Using this information, we can calculate the t-statistic for the null hypothesis by hand. The numerator is the difference between beta 1 hat and beta 2 hat. The denominator is the standard error of this difference, which can be estimated by the square root of the variance of the difference, where the variance can be computed using the elements in the variance-covariance matrix. We can also calculate the p-value for the t-statistic with the t-tail function. All the results are the same as those in the first two methods. Today, we have discussed 3 ways to test hypotheses about a linear combination of parameters. We can rewrite the model so that it contains the parameter of interest. Or we can use the test command in Stata for the original model. Or we can manually compute the t-statistic and its p-value from the variance-covariance matrix. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.